My name is Sam Colosimo, and I'm a student at University of Portland, up in Portland, Oregon. And this summer, I interned at NASA Goddard Space and Flight Center in Greenbelt, Maryland, so shout out to Goddard. And I worked with a group to develop the next generation of X-ray optics, and that's what I'll be presenting on today. So just to give a little bit of a presentation overview, we'll go over some background information concerning X-ray astronomy, X-ray telescopes, then we'll talk about X-ray optic technology development, talk about past X-ray astronomy missions, then we'll go into specifically silicon X-ray optic manufacturing. We'll talk about the manufacturing process, and then we'll go into the mirror assembly process, and then we'll cap it all off with what I did specifically this summer. And then we'll finish with some questions. So to begin, what is an X-ray? Well, it's a type of electromagnetic radiation with a small wavelength, high frequency, and very high energy, much higher than optical light. So just to give you an idea of some objects that emit X-rays, it's really a lot. Black holes, neutron stars, binary star systems, supernova remnants, the sun, even some comets. And X-rays are a dynamic tool for astronomers and researchers. We can learn a lot about the universe from X-rays. In fact, researchers predict that up to 90% of the normal matter in the universe can be seen via X-ray light. So really dynamic research tool. And to just give you an illustration of where X-rays lie on the electromagnetic spectrum, the second highest form of electromagnetic radiation that we know of behind gamma rays, very small wavelength, about the size of a singular atom, much smaller wavelength than optical light. And so you might be wondering, well, how do we observe X-rays? Well, it gets kind of complicated. Because they're so energetic, they pass through most normal matter. And so if we were to try and take a picture of an X-ray with an optical camera, it would just pass right through. So, and then the other thing is that X-rays are absorbed by Earth's atmosphere. So if we want to perform any X-ray astronomy, it has to be done from space with a telescope. So to reflect rather than absorb X-rays, mirrors have to be aligned at an angle that's nearly parallel to the incoming X-ray source. And what we do is there's a primary and a secondary mirror alignment which can take an incoming X-ray and collect it at a focal point some distance behind the mirror assembly. And so the way I like to think about it is it's sort of like collecting an X-ray photon is sort of like skipping a rock across a pond. You know, you get just that right angle and you're gonna collect it. Easy as that, right? So just to give you a further idea of what these things look like, on the left is an illustration of just some photons, red little photons there being collected by an X-ray mirror assembly and brought to some sensor, some location away. And then on the right, what it actually looks like, that's the mirror assembly for NASA's Chandra telescope with human for scale. So let's see here. So when we're talking about X-ray technology, we're really considering, well, there's three parameters that describe the quality of an X-ray optic. The first and really most important is, well, not maybe not most important, but it's pretty important, angular resolution, which is the ability of an image-forming device to distinguish between objects separated by a small angle, and that's measured in arc seconds. 1 arc second is equivalent to a 3600th of a degree. The next is effective area, which is the unrestricted photon collecting area of a telescope. So how big is the image? And then third, certainly last but not least, is the production cost, which, you know, how financially feasible is the telescope? How much is it going to cost the taxpayer? And so to put this in the perspective of past X-ray missions, we have XMM Newton, which was a medium cost, $689 million. But a pretty high collecting area and a decent angular resolution. NASA NuSTAR, again with a fairly high collecting area, 1,000 centimeters squared, less great angular resolution, but much lower cost. And the group I actually researched with this summer created the mirror assembly for NASA NuSTAR, fun fact. Hitomi, which really just wasn't a very good telescope, had a pretty small collecting area, higher production cost than NASA NuSTAR, and worse angular resolution. And to top it off, it blew up after being in space for a month. So just a really bad telescope. Not a bad telescope, but it's okay. And then, certainly last but not least, Chandra, which is like the best X-ray telescope that we've ever put in space. It has sub 1 arcsecond angular resolution, which is the human equivalent of being able to resolve a stop sign from 12 miles away. So just incredible angular resolution, but again, it suffers in terms of collecting area with relatively small collective area and at a very high cost, $1.65 billion. So the problem is that future missions will require thousands of nearly perfect mirror segments to produce an optical assembly with less than 5 arcsecond angular resolution and still having a large collecting area at a price that doesn't break the bank. And so really this is a feat that's impossible with traditional glass mirrors. So to meet these requirements, research has been done in developing a time-efficient, cost-effective process to manufacture single crystal silicon mirrors. And so you might be familiar with silicon from the semiconductor industry, but it's also valid as a material to make X-ray optics, mainly because it has no internal stress. So it's a single crystal silicon, so it has no internal stress. Furthermore, it has a low coefficient of thermal expansion, which is really great for any material you're putting into space. High thermal conductivity, and it's highly available, again, due to the semiconductor industry. And on the right, there's a picture of how a single crystal silicon is made. It's spun into a boule in factories all over the country. And so here is an illustration of the silicon X-ray optic manufacturing process from beginning to end. And so the next few slides, I'll just be kind of going through each sub-manufacturing process and kind of explaining how we can turn a boule of silicon into a lightweight, accurate mirror, which is ready to go up into space. So the first two processes are slicing and lapping. So factories all over the country make these single crystal silicon boules, and they cut them into nice little blocks that you can basically buy online. And once those blocks are ordered, they undergo a slicing process, which basically you imprint that conical form into the silicon block with a CNC mill using a precise cut path. And then after that conical form has been imprinted, it's ready for a lapping process, which lapping in general is the process of rubbing two surfaces together with a loose grit in between them until you have a desired surface roughness. And so that's done by placing these silicon blocks with that conical form onto a rotating metal cylinder and rotating it with that fine grit until desired surface roughness is reached. Next, they undergo another slicing process, which is carried out with a bandsaw. You heard me right, a bandsaw. And people in the optics industry kind of lose their minds at this because they think you're slicing your optics with a bandsaw. But yeah, it's true. And so what's done is thin substrate is released, which will then become become the mirror. And thin substrate, less than 1 millimeter thick. And once that substrate is released, that block can then be used again to create more mirror segments. After that thin substrate has been released, it's ready to undergo an etching and a polishing process. So during etching, mirrors are bathed in a hydrofluoric acid, which relieves any stress that might be remaining in the substrate. And then they're polished on a rotating cylinder with these diamond-shaped pads here, and that gives us the nice second-order shape that's required for the optical design of a telescope, X-ray telescope. And lastly, once it's been polished, the edges are trimmed. There's edge defects that occur on these thin substrates, and so to get rid of them, we just trim off the edges, and that's done with a repurposed surface grinder. So now we have this nice fancy polished X-ray mirror ready to be assembled, basically. And so once they're manufactured, they're added to this mirror assembly, and the mirror assembly is optimized to minimize mass, mirror distortion, while maximizing collecting area, while maintaining the structural integrity that will allow it to undergo the rigors of spaceflight. So to do this, we use something called the metashell approach, which basically is stacking mirrors on cylindrical supports separated by these small silicon spacers, and several different metashell sizes are then aligned concentrically, which then create the final X-ray optic mirror assembly ready for space. And so specifically what I worked on this summer was one process of the manufacturing, which was the lapping tool. So the first thing I did to expand the process, the group that I worked with is continually trying to build more machines. So I got to build a lapping tool machine myself. And then one of the problems that we were faced with was, well, how exactly do we know the diameter and the exact shape of these conical tools? It's important that we know the shape so as to produce the mirrors with the way we want, basically. And so I devised a measurement technique that can be used quick and easy to get an idea of what the large and small diameters are on these conical tools. And then really the second thing I worked on was involving the mirror assembly process. So during the assembly process, like I said, each mirror is bonded to 4 silicon spacers. And so this bond must align each mirror segment basically perfectly. And it must be preserved, again, throughout the rigors of spaceflight. So we want a good bond. And so the question that my mentor posed to me is, which epoxy is going to work best for the job? And you can go online and research all these epoxies, and they'll tell you what the strength is, but more than likely, it's not going to be what the strength was with the material silicon. Most likely it's aluminum or steel, so obviously very specific testing was required to get an idea of which epoxy works best. And so I designed these test fixtures that could be used with a tensile test machine to perform tensile and lap shear tests. So essentially, you have these 2 fixtures that grip small silicon spacers that are glued together and pulls them apart, and we can get an idea of what the strength of that epoxy is when bonded to silicon. And so just figuring out that entire process and designing some test techniques. So in conclusion, some improvements were made to the manufacturing process via building a new lapping machine and minimizing the time necessary to get those conical tool measurements, and then also further researching into the mirror assembly, specifically what epoxy is going to work best when applied to the material of silicon. So yeah, anyone have any questions?